question how to keep our waters clean is very universal and actually very relevant to Switzerland because we have a lot of lakes and rivers. Please give a warm welcome to Paola Bianchi and Silvan Melchior, both data scientists at Zühlke Engineering AG. Please, the stage is yours.
Thank you. Welcome to our talk, Keeping Waterways Clean with Machine Learning. As just said, I am Paola Bianchi. Oh, sorry. Now you can see it. And he's Silvan Melchior. We are both data scientists at Zühlke Engineering, and in the next 20 minutes, we're going to present you a project we had a couple of years ago with PUB, that is the Singapore's Public Utility Board. Their responsibility is managing the water supplies, the water catchment, and in general monitoring the usage of water in Singapore. Their main challenge about waterways is to make sure that water in Singapore looks like this picture and not this picture. And apparently one of the main causes of this effect, so water pollution, is poorly planned construction sites. So like when a construction site isn't planned in the proper way, then when there's a heavy rain, dirt that is in the construction site drifts off and goes into the waterways. So it's very important that companies that do construction plan in a way that prevents such things. So they have to submit a plan that is called earth control measures. So they have to make sure that they take the proper measure to avoid this. And for example, so if once they submit such a plan, this gets checked by PUB, and if it's compliant, then it means that it's safe. If it's not compliant, there is actually a risk of pollution. So how do they check? They have a bunch of rules. So in this case, for example, the hoarding forms a closed loop and is sealed at the bottom. What does it mean? That they have to see in this plan, first of all, from the above view, they have to check that the area that is exposed has a hoarding, and it goes all the way across, and it is sealed at the bottom, so it's the water, dirt cannot filter through the bottom. So there's a bunch of checks involved, like which part of this plan is important, what text is important, what elements are important. And this check is done, normally was done manually by employees of PUB. And they have quite a lot of drawing submissions. So of course, this is a time-consuming and resource-consuming process. So the request was to completely substitute this human process with AI, and that's the request they came to us with.
Yes. So we have seen these plans, which was shown by Paula before. This was like the expectation which we went into the project with. These plans, nicely drawn, nice figures and so on. And so this is also what we expected when we started the project. Well, very naive, of course. Reality is very, very different. So we looked at the data we got, which was very different from the data we got when we estimated the project. But like it was really, the complexity was huge, much larger than the plans we have seen. Like the notion was all over the place. People used completely different symbols for different things. There were 10 different names to name the same thing. There were like some people had tables to cover information, others had it as free text, others had it attached to the email. Like it's really crazy differences. Then all these elements overlapped, so sometimes this was a nice drawing beforehand. Sometimes it just had like a Google Maps printout and then drawn on top how this will look like. Very bad resolution and a lot of spelling errors. So it took not a lot of time to find out that this nice vision of fully automating this is completely unfeasible. And so we found, okay, what do we do? Well, if not an automation, maybe an augmentation. So how about we make it possible that we check what we can check and let the rest of the part to the human. And with this, hopefully still save time. And so the goal of the prototype was to find out how well does this work? Do we save enough time that it's actually worth to do so? Or is it just some useless solution which in the end you don't save any time? So how do we do this? Is this your part?
Yes, so this is kind of the overview of the automation process that we planned. So starting from the PDF, we have a machine learning part that does a few things. First of all, we need to extract the different views from the plan. And then we have both drawing, like element recognition and text recognition with OCR. And both of these parts come together in a deterministic rule checking. And then the result of this is presented in a user interface so that an expert can validate the results. So for the view extraction, by view, I mean all these different parts. So you have a top view, a side view, a legend, and these need to be separated because we have different information in each of these views. For this, it was quite easy to annotate this, and we use a detection tool to detect this part. For the OCR, we use the AWS textstruct to recognize the text, and then we had to do some post-processing because both because of the limitation of the method and also because of the issues that Silvan mentioned before, so issues with the resolution and spelling. So we needed to do paragraph grouping and spelling correction, and also with text in different orientation that was not out of the box from textstruct. Yes, for the element recognition, so this is the visual parts in the plan, we had to separate between two different types of elements, and they are called things and stuff. I did not make this up. This is actually how they are called in the literature. And things are elements that are countable and localized in an area of the plan. Like, for example, the storage pond, the treatment plant, like it's, for example, a rectangle, and it's you can see it there. While stuff is more an area spanning through the drawing. So, for example, in this case, the hoarding, but also like the exposed area. So it can have a very weird shape, and the exact shape is very important. And we needed to use two different approaches for this. So we had, of course, for things it's easier, and we could do instant segmentation with detection, but that did not work well for stuff. So we tried different models, and in the end, UNet gave a better result with semantic segmentation. Yes.
Then we have detected these elements, we have detected the text, and now it's about putting all of this together. So we have, for example, detected maybe a hoarding, we have detected some text, and now we need to find out, we have detected some treatment plant, and then we need to find out, does this hoarding form a closed loop? Is it around the treatment plant? Has it a sealed bottom? And so the last part was the rule engine. This was really pure software engineering, trying to figure out, based on the previous detection, what works and what is not working. So there are different types of rules. The details are not so important here. Some are more about the position. It's like the hoarding around the side. Some are about the numbers. Is the number of storage ponds and the number of treatment plants equally? So do we have for every storage pond also a treatment plant, such that if the water goes into the storage pond, it gets treated by its separate plant? And then some values, for example, you have a runoff volume based on the exposed area, and then you assume some rain, and then you know what's the water and the runoff volume, and then you want to see whether the capacity of the storage pond and the treatment plant are large enough that if there is even heavy rain, that they don't overfill these things. These were more classical computer vision approaches. Just one example here with the hoarding, because it's so nicely visual. We have here the instance segmentation detections of the hoarding. We have the semantic segmentation of the storage pond. Now we want to find out, is the hoarding closed, and does it not, is this some phone? Does it not touch the storage pond? And so what we do is we do a so-called flood fill from computer vision. You know it, you like color one pixel, and then you color all the neighbors of these pixels which do not touch the hoarding. And then if in the end the storage pond is dry, then you have one. And so these are like types of rules we implemented. And then after all of this, we had the full pipeline together and we started to evaluate. And well, the expectation of the client was somewhat like confusion matrix like this. So for every plan, we have some rules, and then the algorithm says, well, for these 20 rules, these few passed and these few failed, and then there is also ground truth, like the experts looked at these plans and said, well, there is still an issue with this, this, and this is already satisfied, and then they expected that this works just perfectly. Reality was more like this. It was not like useless, but it was also not great. But that's not very unexpected. As we said, we knew, well, this is going to be a hard problem because this is still full automation. And this is why, okay, well, let's relax the problem a bit. Let's not just try to say for every rule that this is passed or failed. Let's also allow a rule to say, I don't know. So for example, in this filling, like flood fill, if there are just some small gaps, then let's do 2 flood fills, ones which have an eroded boundary and one not. And then if it touches in both cases, then it's for sure failed. If it's only in one case, then it's unknown. And if in both cases it doesn't touch, then it's passed. So we changed these rules to allow to also say, I don't know. And well, why should we do this? Well, actually, first of all, this is also true in reality. Sometimes we just don't have the information. Sometimes information is missing in these plans, and so you actually don't know. And second of all, sometimes the information is provided, but we can't just evaluate it. And so the costs of this confusion matrix here are somewhat like this. So if you have a correct prediction, if you say, for example, it's true and it is true, then it's great. If you say false and it's false, it's great. If you say, I don't know, and actually you cannot know, that's great. But this is only part of the story. If you say, I don't know, and actually you should have known, then it's not great, but it's also still okay. If you say, well, it's false, but actually it's true, that's also not great, but still not that bad, because then the engineer or the expert will look at it and say, well, actually, no, this is true. And what's really bad is you say, well, this is working, this is perfect, but actually it's not working. And so we have these costs, and we can tune the rules. And we adjusted our algorithms to make it then more look like this. We cannot, unfortunately, provide numbers here, like this was not desired by the client, but it was possible to get most of the mass from these unfortunate predictions here to the I don't know case, and then very often the algorithms just said, I don't know, instead of a wrong answer. And so this was a really nice line, much better than before. And so we built a small UI. We built this all in AWS, so here is quick the architecture, how this looks like. We have a front end, we have a back end with Fast API, front end with React, and then we used AWS Amplify to build all the UI parts, and then we have some VPC and the application load balancer. How does it look like? This is one example of this UI. We have here blurred the plan a bit because it's from some client, and this is like the perfect case. You upload the document, then a lot of things are checked, and then in the end you have the huge, is this accepted? You have then some of the detections which you can look at here. You can, for example, say, well, where is the legend? And then it shows the detection. You can say, where is the timber post? And then it shows you the segmentation of the timber post. You can do text search and say, well, where is the runoff? And then it shows you the runoff volume. And so this helps you to check it. In reality, plans look, of course, like this. And then you have, like, for example, a reject because some of the rules failed and some passed. And then you can look at each rule. You can say, show me all the relevant stuff. And then it zooms to the part which is detected, which should evaluate this part. And then you can decide to override this rule or to leave it like this. Yes.
Mm-hmm. So what are the next steps from here? Yes, so the main goal for this project was also to evaluate whether it was possible to provide such a solution with AI. And as you could see, fully automation is not feasible. So what we suggested in the end was to reevaluate the business case so that it would be helping the expert instead of substituting them. What we also suggested was to standardize the submissions, so enforce some standards. For example, the treatment plant should always be a rectangle, so you don't have like once a yellow rectangle and once a blue circle, and that would, of course, improve also the metrics of the models, and only after start building the MVP. Yes, I would just finish mentioning that we have a booth in the main room. So if you want to know more about this project or any other project that we do at Zühlke, please come visit us. Thank you.
Are there any questions from the audience? I do have one. In the meantime, you can think about another question. Do you have general knowledge that you could apply or pitch to Swiss clients?
From this
Yes,
case?
from this Singapore use case, use it for Switzerland.
I mean, a lot of people say it, but it holds true. There is this garbage in, garbage out saying. It was not garbage, but I mean, if you have challenging data and not a lot of it, there is not so much you can do. At least, I mean, this project was 2 years ago. There was not, foundation models were not a big time back then. Now, we might have done this project a bit different maybe, because with foundation models you can also gain insight from a much smaller amount of data. Like if, for example, segment anything, we might have been able to solve the segmentation much better. But in general, yes, I mean, data is still often a bottleneck. And in this case, this was the bottleneck. You could do the most fancy algorithms, but you were very limited with the data in the end.
And let's pretend Swiss data is better. Could you do the project faster?
Yeah, so one other thing that appeared here and is quite common in projects is managing expectations. So whenever a client comes with, we would like machine learning to do everything and we don't even check, that is usually a red flag. And we tend to also advise in similar solutions. So slightly change the business case and provide something that is auxiliary instead of replacing.
Thank you. In the meantime, we have a question.
Yeah, maybe I have an answer to your question here. They can use, I heard, I've never done it, but I heard that Baupläne is very tedious work. Whenever you want to, build a small thing in your house, you have to wait for a year or more to get the approval. So maybe you can go and sell your product to those Bauamt or something. Another question I had is how does Singapore come to Zühlke? I mean, why didn't they get some company from Singapore? I mean,
we have offices in Singapore.
Ah, okay,
yes,
okay.
Yeah. And Hong Kong and Vietnam.
Ah, so okay.
Do we have another question? Yes, at the back.
Just a short question. Maybe you can elaborate a little bit on this. You adjusted your confusion matrix there. Can you tell a bit how you did that? You adjust your loss function, or you used probabilities there?
So we don't have real probabilities because these rules were more like classical software engineering. Then you have this flood fill and it touches or it doesn't. You can then have some heuristics to get probabilities. But in the end, it's really, we have maybe 30 plans in the test set. In each plan, we check 50 rules. Then you have 150 data points where you have some prediction by the algorithm. And you have, 1,500. And you have the same amount of annotations by the experts from the past. And then you can really just calculate true positive, true negative, and so on, and count these and create the confusion matrix.
Should we also continue the applause for both of that? Let's do that. Thank you so much. Small gift from us.
Thank you.
Oh, not my cards. Thank you so much. Please visit the booth and continue the discussion.